Welcome back to another Ramda JS video, and in this video we are going to talk about the pretty cool function evolve from the Ramda JS library. But before we dive into that, let me just mention first that I want to amend a error that was made in the last video. So SEO Camo, who's been following along with this series quite intensely, which I'm very glad for, made a comment in regards to the last video that I let me just read this comment, right? It's like the eqprops function that I was defining is not pure, and it takes p1, the variables p1 and p2 from the outer scope, and only actually uses the first argument. So first I thought, wait, what is he talking about? But then I read what I had done, and then it turns out that if I make videos that are 1 hour long, then apparently I get too confused to think straight, right? So it was an extremely silly mistake, and the comment is completely accurate. So let me just close this and jump into Node and just show you what I did. So I did something like this. Like in the last video, we looked at equality, and we talked about the three equality functions, and then we talked about this eqprops function. Let me just start by requiring Ramda here so that we have it here, right? And then just let's see if I say eqby, do we have that function? Yeah, okay, so we've loaded Ramda, right? And what I wanted to do is I wanted to define the function eqprops through composing the Ramda function prop and the Ramda function eqby, right? So I defined it something like this. I said let eqprops be r-eqby r-props, or sorry, I mean it's a function that takes some x and then says, is it called props or prop? Let me just check. If I search for prop here, it's called prop. Okay, let's go back to evolve later. Okay, and then let's close this. So prop over x. So this, like exactly like this, that's what I was intending to do, right? That was sort of what I had in my head. Unfortunately, however, I also used two variables that were in scope. So I immediately passed p1 and p2, which were the two objects that we were using, the two objects that that we wanted to compare equality between. And then of course I used, like, if you, as you can clearly see now, right, if we only look at it like this, we don't have p1 and p2 in scope, right? And that's why he was saying that it's not pure, which makes perfect sense, right? Because p1 and p2 existed in the scope of that sort of REPL interaction, right? But now we don't have that. Like if I just do this, then I mean, okay, it works, but p1 is not defined and p2 is not defined. And if I try to call the function eqprops by, let's pass id, and then let's pass some object with an ID 1, and then another object with an ID 1. It's probably just going to crash. Right, so it crashes because p1 and p2 are not defined. But in the other one, it worked because then we actually referenced the variables that were in scope. But anyways, what I was trying to do, right? Let's jump one row here. And then what I was trying to do is essentially just this, right? That's what I was trying to do. That would work, right? It's like we're... sorry, okay, let. I reused, I've already declared the variable, so I just have to say eqprops equals, right? So like that, right? That's what I was intending to do. Because this you can use, so if I now call eqprops like this with these two objects, you can see then we get true back. And that's what I was expecting. Sorry, I'm not explaining this in detail because I'm just assuming that you've watched the last video and that this, of course, is an amendment to what was wrong in the last video. And if I change the ID of one of these objects, you can see we get false back. So that works. So yeah, sorry about that, right? And you can also notice how I'm calling this function with this sort of explicit partial application, right? Like not with the sort of comma syntax. I'm not calling it with multiple arguments, but I'm calling it as like we're first calling it by applying it to ID, and then sort of using the parenthesis syntax here to sort of apply the function that's returned to the next two arguments. And of course I can't do this, unfortunately, right, with our implementation of eqprops. To do that, I can, however, just use uncurrying from Ramda. So I could say r uncurry n, and then I'm gonna need 3 arguments, and then we pass that other function and then close that, and now we should be able to call it this way, right? This way and this way. Both of them work, right? And of course, let me just pass some stuff that actually satisfies the condition, and then you can see that works. Sorry, I have to just let the cat in. Okay, So that was a quick side note. Let's drop this and let's keep going. Hopefully you can see how that worked. And yeah, that was an amendment to the last video. You could probably, again, as I was mentioning in the last video, you can also probably make this function point free, because now we have this x variable here, but you could probably get rid of that. And that, I guess, would be an interesting exercise if you would want to try that out and see if you can make this function point free. So let's now leave ecprops. let's leave equality. So let me jump out of the REPL here. Let me clear the screen, and let's scroll down to evolve again, right? So this is actually the function that we're gonna talk about. So what does evolve do? It's pretty cool, right? What it does is that, let's just read the definition here. It creates a new object by recursively evolving a shallow copy of object according to the transformation functions. Object here is then, like, you're passing a transformation object and you're passing some data object, and you're evolving the data object on the basis of your transformation object. And then they're saying, okay, all non-primitive properties are copied by reference. So non-primitive would mean a function, for example. But I guess instances of classes as well. That should be non-primitive, right? Because objects are primitives, right? But if you have an instance of a class, that should probably be a non-primitive. So that was interesting. I didn't think about that, but okay. And then the next one, or the second portion here, says that a transformation function will not be invoked if its corresponding key does not exist in the evolved object. So if you're not so if you have a transformation function that doesn't, so if you are saying transform this particular property, but that particular property doesn't actually exist in your data object, then, like, the thing won't crash. It will just ignore that transformation because you haven't actually supplied that data, right? Which kind of makes sense, right? So have a look at this example here, right? It's a bit messy, and especially because my huge font size, so we're in need of line breaks. What I'm actually going to do is I'm going to jump into Vim and open up a main.js file, and then we're going to write this in a file, because I think that's going to be easier also when we try to redefine evolve ourselves as well. So let's just say we're requiring Ramda, and let's just console, as usual, let's just console log R.evolve, just to make sure that we've set up everything correctly. So let me just map a keystroke to running this file through Node, and then you can see we get back a function here, so it seems that this sort of works out. Okay, so we have evolve, right? Let's look at that. Let's look at the type signature here. Okay, so the type signature says that you have to pass. Let's just start in this end, right? There's one argument here, then there's one argument here, and then you get something back. Okay, and then let's look at it in more detail. This first thing is the transformation function. The second thing is the object, the data object, and this third thing is, of course, then the returned data object, the transformed data object, rather, right? Like, first you pass the transformation object, then you pass the data object, and the thing you get back is the data object ran through or evolved through the transformation object. And then let's look at, I mean, this type definition is actually very, very informative if you think about it, right? Because what they're saying here is that, like, assume in your transformation object that you have some keys that belong to the type k, right? Like you have the set of k, which are the keys, and then you have some values, right? But that are the values that the keys map to are functions that map from v to v, right? And v here, presumably, like, they're using that to denote that it's a value, right? I mean, it doesn't really matter, but, like, for semantically, they probably chose the variable k and the variable v, the type variables k and v, to indicate to us that we should think of this as a key and we should think of this as a value, right? So all the keys point to functions that map from something of type v to something else of type v. Okay, that's the whole first argument, and that's the transformation thing, right? So it's an object that contains a bunch of functions under keys. And then the next one is, like, argument 2 is also an object that contains keys as denoted by or that are from the same type, right? So also keys of type k, and then values of type v, which means that you can, of course, map. You can say, well, okay, in both of these cases, I have keys of type k, and in the second argument here, I have values of type v, but in the first argument, I have functions that map from values of type v to something else, which then now happens to be values of type v as well. So it's sort of implying to us that, okay, this is the data, and these are the transformations, and what we're going to do is we're going to take the transformations and apply them to the data to get some new data back out, right? So it's kind of like, you can think of this as map, right? It's like we're saying, well, this is the mapping function, right? But it's a sort of a boxed mapping function or collection of mapping functions, and this is the sort of container of values, and then this is the values that we, or these are the values that we get back, or this is the value that we get back. But so let's actually look at this, right? Let's do something not so sensible. So I'm not going to do anything that's the example is going to be slightly contrived, but whatever, right? So let's say we have some data, right? Let's say data obj and trans obj, maybe. Let's just say data and maybe transformations, right? Let's say data and transformations. Okay, so the data is maybe something like this. Let's say we have a name, a name key that points to an object that contains first, that points to a string. So let's say John, and then last, and then let's say Doe. And then let's say maybe we have something like friends. And maybe that's, so now I'm doing this overly complicated, but let's just do it this way, right? So there's another key which is called friends that points to an array, and maybe that contains like Jane and Jenny. I don't know, right? Whatever, okay? So that's some data, right? And then we have some transformations. So what we can do with these transformations is that we can construct a number, we can mirror the keys in this data object recursively, right? Like deeply, quotation marks. So we can like notice how we have things inside of things here in the data, right? Like it's not just a shallow object where you have name and then, wait, did it say recursively evolving a shallow copy of object? I wonder why they say shallow here in the description. Let's think about that, because you do actually go recursively, of course, recursively evolving a shallow copy. Probably it has something to do with they're trying to emphasize that if you mutate, you'll mutate a copy and not the original structure. Maybe something like that. Not sure. I guess that's why they're emphasizing that. So it's like, well, be careful and don't mutate and assume that you will be able to mutate the outer thing, but actually you can't. But also maybe they're saying that to emphasize that. Maybe they're also saying that to emphasize that if your transformation functions are mutating, then you might be inadvertently, or like without intending it, you might be mutating data inside the object. So your transformation functions should be pure, which they should be anyway, right? But at least then you know. Okay, or at least they should treat all structures that it's being passed as immutable. It doesn't necessarily have to be pure if we're being a bit pragmatic, right? Like you might want to use randomness or whatever. That's totally fine, right? Anyways, let's dive into it. So okay, we have this data object, and then we have some transformations. So then the question is, like, what are the transformations that we're going to do? Well, firstly, we need to reflect the structure here. So we're going to say that we have a name object, and inside of this name, or we have a name key that points to an object, and inside this name object, we're going to have first, and we are going to have last. And let's just put the identity function, just to emphasize that that works, right? And that you can use the identity function. So friends would be r dot. Here we probably have to say, or actually we could say identity directly, right? Because an array is a value, so we don't necessarily have to consider the array a collection of parts. We can just consider it a single thing, right? So what now, right? Now I can say evolve, using these transformations, evolve the data. And what happens if I run this? Well, actually, maybe I should first console log the original data as well. So let's console log the data, and then let's console log the transformed data. And then maybe a line break between them. Okay, so here you can see, here's the original data, and then this is the transformed data. And of course, they look exactly the same, right? Because they both are because we use the identity function as our transformation function everywhere. But what if we don't use the identity function? What if, for example, for first we say toUpper, right? I think toUpper is a Ramda function that makes something uppercase. Yeah, toUpper, right? And what if we then, let's do more at the same time. What if we for last say to lower, right? So notice it's not lowercase now. Do is with a capitalized D. Let's run that and see. Okay. Now you can see the output is actually, the transformed output is actually different from the untransformed input, from the original input, right? We have first pointing to John with a capital J and then last with a capital D. But then after it's transformed, we have first and then uppercase John and lowercase Do for last, right? So we're actually successfully applying our transformations. But then we still have the friends, right? We still have the friends as usual, because there we use the identity function. And I wonder if I just remove this transformation function, do we get that data or do we not get that data? Yeah, so it's not like it's removing data to which we're specifying. It's not like evolve is removing data from our object just because we didn't specify a transformation function. So not specifying a transformation function and specifying that the transformation function is identity is essentially the same thing, right? From the perspective of evolve. However, also let's establish that point that they said here. Let me close that. They say a transformation function will not be invoked if its corresponding key does not exist in the evolved object, right? So you could also have, like, let's say there's another. We're saying that there's a transformation function for keys called foo that, I don't know, like does, well, let's just say toUpper here as well, right? It doesn't matter. So it's going to apply toUpper. Well, let's just say, I mean, let's do something else. Let's say add to that, right? So it's like, we're assuming that foo is, let's say age maybe, right? So we're assuming that age is a number, and then we're going to add 2 to that age. This makes no sense, but whatever, right? If I run that, you can see it works fine. We still get back the same data and all that stuff. Like it doesn't crash just because we have a transformation function that doesn't correspond to any data in our actual data object. But if we did have something like that, right? If we did have an age, let's say 12 here, right? If I save that and then run that, then you can see it does apply the transformation function to the data, right? So you're pretty safe in that end. It's like, even if you're specifying a transformation function in the absence of data under that key, it's not going to crash and it's not going to run the transformation. And even if you have some data to which there is no corresponding transformation function, then it won't crash either, and it won't forget to bring along that data for you, right? It's going to bring along that data for you. It's as if the transformation function was identity. But let's stop here, and then let's do some more stuff, right? So hopefully you can see how this works and how it's actually like pretty powerful, because it sort of works recursively. So you can very trivially transform objects sort of any way you want. Not any way you want, but I mean, hopefully you can see how this is very powerful. Okay, one thing I want to show also is that, of course, friends here is an array, right? So an array is something that's mappable. So instead of just saying identity, what we could say is that we could map a function over that. So we could say R.map, and then let me just think about it. I guess that's the way we would have to do it. I guess that they are not sort of unfolding arrays or mapping for us. No, let's do it this way, right? Let's try this out. So what if we said R.map R.identity? This should work. Yeah, then we get back the same thing, but we are now saying that we want to have the same, like we're saying the transformation function for every element in the array is identity, which is different from saying that the transformation function for the whole array is identity. Right? Those are two different things. So that's cool. That works, right? But we could also then now say R.toUpper, for example, inside the map, which would then give us every element here uppercased, right? Or like, let's say obj of person or something like that, right? I think that works, right? So then it's like, or maybe it should be, yeah, or whatever, name. Whatever, right? It's like, so then we're turning the friends into objects, right? So the friends array now contains a bunch of objects that have name keys that map to some particular string. So anyways, this is a pretty cool function, and I hope you can see how this can be sort of useful. Before, I mean, we're going to wrap this up, but before we wrap this up, I just want to take the chance to implement our own version of evolve, right? So not like any special kind of or it's like so maybe what I should say is this: if we jump to the source of Ramda and look at the implementation of evolve, I think it's interesting because, again, like as usual and as should be, right, what they are doing is that they are of course implementing the sort of most efficient version of the algorithm. And so they're not necessarily thinking about immutability or like about the implementation being elegant or like about using composition or like whatever, right? I mean, it's like, or like necessarily being functional or even not mutating. Maybe this I already said, right? But you can see the point, right? They have an efficient implementation of this particular function. Now, could you write it using composition? Of course, right? So let's just think about how to do that. So if you want to run evolve, like if you want to have an implementation of evolve, we need two things. We need some transformation functions, and then we need some object, right? So let me just call that T and O. And actually, I think we're going to be able to do this using the second portion as a point-free function. So let me just say T here for the transformation functions. And then we're going to use, I can't remember if we've used this function in some other episode, but I don't think we've talked about, wait, CDE. Yeah, no, exactly. We haven't talked about it as a separate video, right? But there's this function mapObjIndexed that's essentially map for objects, where in every iteration of the map you not only have access to the element inside of the object that you are currently at, but you also have access to the key under which that object resided, I guess. Resided, right. So I'm not going to go into in detail, but I think you can see how this works if we try this out, right? So what we could do is that we could say, well, okay, map over the second object that we're about to be passed, right? I could even make it non-point free just to make it a bit more explicit, right? If we are being passed T and then, let's say T and then O, so the transformation object and then the data object, then we would say mapObjIndexed, and then we would do something inside of here, and then we would pass O, right, in the end. So okay, what's the implementation, or what's the function that we're passing to the mapper here? Well, for every element here, for every item in the object that we're mapping, there would be 3 variables, as we can see here. Again, we'll talk about this in some specific video, but and that'll be like the number. Oh, sorry, now I just read immediately from here. It will be the value that we are currently at. We'll get the key under which that value resides, and then we will have the whole object. We'll just have a reference to the whole object. I'll put underscore as a variable name there, just to emphasize that we don't care about that argument, right? Actually, sorry, because this is a 3-arity function, I could probably just do that, and that'll work still. Yeah, so let's do that. Okay. So those are the two arguments that we have, and then we're gonna do this, right? So maybe let me put should I put a line break here? Maybe here. We'll figure the syntax out later. Okay. So, and what are we gonna do then? Well, it's actually pretty simple, right? Because we have to do some recursion, but we also have to say, okay, what we have to know is whether we should recurse or whether we are at a primitive, right? Are we at an object, or sorry, not at a primitive? I mean, are we looking at an object currently that needs to be further unfolded, or are we looking at a value which needs to be transformed, right? So what we can do is simply we can say, well, let's check our transformation object, and let's check what the value is under the particular key that we're at, and let's ask for the type of that, right? So what's the type of that thing? And let's say, does that equal object, right? Is that an object? Because if it's an object, then that means we need to recurse, right? So let's say, well, then we need to return the evolving of whatever is under, with that object as the transformation function in the next step, and then the value as the object that needs to be transformed. So we're diving downwards, right? So think about that for a moment, and let me just let out the cat. So it's not the end of the world if you're not getting that, but just try this out and sort of toy around with this example yourself, and you will see why this works if you're not getting it immediately. But yeah, so that's what we will do in the sort of recursion case. But then the question is, well, what are we going to do in the, maybe I should call it base case, maybe I shouldn't call it base case? It's not really a base case, but whatever. No, it actually, yeah, sorry, it is like a base case. What should we do in the base case? What should we do in the case where we don't have something that should be further recursively evolved, right? Something that needs to be unfolded further. Well, if we have that, then that means that the thing under tk, the value inside our transformation object at the key that we are currently at when iterating through the transformation object, or sorry, when iterating through the data object. Okay, when iterating through the data object, we will at any given point in time be at a particular key, right? Such as name or first or last. And if we happen to be at last, that means that in our transformation, we will have a function here. So last will point to a function, which means that that thing will not be an object, which means that we should take that function and apply it. If, however, we are at a name, for example, then that means that the value there will be an object, which means that we can't take that object and apply it because it's not a function. So what we need to do is we need to dive downwards through that. So we need to take, we need to recursively call evolve with these, like with the value under that key as the transformation object for the next step, and then with the value under that key from the data object as well, because that's the thing that needs to be transformed or evolved. So that would be this portion, right? Like the object containing first John and last Doe. And so that was this case, right? That was line 23. That was the recursive evolve case. But again, like if we are at first, or if we are at last, or or if we are at friends, then that means that we have a value. We don't have an object. And that means that we should simply take the thing under the current key in the transformation object, which would then be either to upper, to lower, or this mapping function. And all of these are functions. So we should simply just take that function and apply that function to the given value that we are at, right? This should work, right? So let's remove this r dot here in our console logging so that we're switching to the function that we've defined ourselves. And let's just run that. And you can see it works exactly the same. So what I'm looking at is this line and this line, right? So I mean, this is the execution where we were using our own function. This is the execution when we were using the Ramda function. But if we look at the transformed output from when using the Ramda function and the transformed output from when using our function, it's the same, right? Of course, maybe there are a bunch of let's say edge cases, or there might be some more things that you might want to have a look at here, because I'm not sure that we are actually covering all the things that they are. Whoops, now we're in the wrong place. Let's go to, what's it called, evolve, right? I'm not sure we're covering these two things that they're saying, right? Non-primitive transformation function will not be invoked if its corresponding key does not exist. Like, I mean, I'm not sure we actually support that. France, no, okay, so we do support that. And there was one more thing, I can't remember this other thing, but otherwise, I mean, I think they also do a bit more checking, right? They do also do this check, so they check that your transformation function actually is a function so that they won't crash. I think it's like if you, no, but maybe that's for other reasons. Yeah, that's in order to run that. And so if it's a function, they run it. They have 3 cases. That's what I get confused about, right? Because we have 2 cases, or 4 actually, right? So if it's a function and they run it, otherwise, oh yeah, they have 3 cases. Otherwise, if it's an object, then they evolve it further. But if it's not a function and it's not an object, then they just pass that on. So that would be, for example, I guess like classes. So why they wouldn't pass that to functions, I'm not entirely sure. But actually, no, wait, sorry. Actually, if you have an object, yes, or sorry, if you have an instance of a class, that should also be an object, or if that would type check to an object. Let's just check that, right? So if you have a person class that has a constructor that takes some name, and then we'll say this dot name is equal to n. Oops, let's say for example, and then let's say console log new person John, whatever, right? This gives us a person whose name is John, right? But if I do the same thing, but I put some parentheses around here just to make that a bit more clear, and then I say type of, what's the type of that? Yeah, so that's actually an object. So yeah, no, they would actually unfold, or wait, is it strictly, yeah, it should be strictly equal to object. Yeah, it is. So they will actually evolve those as well. So then the question is like, what is a non-primitive? Non-primitive primitives JavaScript. Let's just look at that. Maybe that would be an array. No, but that's not true also, because we can see that. No, I was going to say that we can see that that's being unfolded, but that's also because they're doing the function check first. Object references, non-primitive, so just like random blog post, mutable data types, the value of an object can be changed after it's created. No, okay, so actually, yeah, okay, sorry, so arrays are, yaha, okay, sorry, so that's the point. Okay, so they're not saying that it's a special case that non-primitives are sort of not applied to functions. They're simply just saying that if you have a non-primitive, then they will not construct a copy of that non-primitive for you, right? So if you have an array, they will pass your actual array, so that if you are being careless and if you are mutating in your transformation function, again, back to that point, then you will actually mutate your underlying array, right? So that you're not expecting that wouldn't happen, right? But yeah, so it seems to me that that's what they're saying. And then this thing, I don't know, why would this happen, right? It's like, yeah, okay, so then they're just, yeah, no, sorry, okay, so this case is just that if you don't have a transformation, okay, maybe this is just because they wrote their implementation differently from the way, yeah, okay. This is probably because they wrote the implementation differently from the way I wrote it, right? They have to copy over the thing, right? So either they need to transform the thing, or they need to evolve the thing, or it's the same, right? It's like if you have a transformation function, then run it through the transformation function. If it's an object that contains further transformation functions, then you need to further evolve that, and you need to recurse. But if you don't have a transformation function and it's not an object, then it just needs to be copied, right? We didn't have to think about that thing because we used map. Right? We mapped over the original object, whereas they are just actually constructing a new object and copying over data. Right, and that's probably why they're saying it's a shallow copy also. Okay, so that makes sense. It's just an implementation detail, right? It's not that they have another case. So I think maybe we cover quite a few cases with the implementation that we wrote, but who knows? Maybe there are some things that we are not covering, and if you can think of anything spontaneously, do let me know in the comments. That would be interesting to see what we are missing. Of course, there are more elegant ways of writing this function, right? And I mean, one thing that one thing we should do, for example, is definitely that we should curry this function if we wrote it like this, right? So we should say it needs, yeah, okay, we should probably be able to just say like this, right? Yeah, that works the same way still. And then we would be able to call it like this. Yeah, but I mean, there are many other ways of writing this function. You might, for example, remove this these two and just take the first t and then not apply the o here, because whenever you have that case, right, whenever you have the case of that you're taking an argument and the only thing you're doing with that argument is that you're applying it in the end, then that means you can remove that quotation marks point and just like run the next function. But that would mean that this particular syntax that we have now is not valid. Then we need to run it like this, right, with the sort of parenthesis syntax, and that would still, whoops, I said that would still work, but it didn't actually work. T V, aha, why did this not work? Transformations, what did not work? Name was not recursive. Yeah, okay, sorry, because then our recursion also needs to be called like this, right? If we run that, then you can see it still works fine, right? But then we might want to say, again, like, but now we have a curried function, so then we might want to say uncurry with 2 arguments, so that we can call it using this sort of comma syntax, or like with multiple arguments as opposed to using partial application. Now that works as well, right? But there are probably tons of other ways of doing it, and I guess there would be a way of making it truly point-free so that you don't have this t here, or probably other ways using composition or whatever. But okay, let's not go there. As usual, thanks a ton for watching. Hit the like button if you appreciated this video, and remember to subscribe so that you won't miss upcoming videos. I'm glad to have you along on this journey. I'll see you on the next one. In the next one.